properties are really important. And there is like one quote which I really like, doesn't matter if it's true or not, and it's like 1 kilogram of the satellite is equal to the price of 1 kilogram to the gold. It basically said that you have to be aware where you put the mass on the satellite. Then we have static and dynamic volume or envelope. You can imagine it as a virtual box, and you have to fit the satellite into this box. You can never exceed this box. Then mechanical interface. This is also something really important because you have satellite and you need to put it into rocket. And the mechanical interface is thing or the face of the satellite, which purpose is to attach like into something, but in this case into the rocket. So basically the most common way is drawing with, for example, 4 holes and with the diameter of the hole. Nothing complex. Then the last thing is positional tolerance. This is really also important because when you design a structure, you have a lot of parts. And those parts could be made from different suppliers. Yeah, and you have to be able and you have to ensure that you will like assemble this satellite. So you need to put some tolerance in it. And the suppliers have to provide it. Also, when you have a satellite, you can have some payloads which you need to have positioned really correctly. For example, a camera. So when you want to, let's say, capture Czech Republic, you need to know the error of the position. Then you can compensate it. All right. Now, when we know what the requirements is, I would like to tell you something about differences between space sector and other sectors, because it is a difference. And the biggest one is that when you make a satellite and you make a mistake, you send it up to the orbit, you cannot go there and you cannot repair it. Okay? You cannot buy a ticket to the orbit, go there, just fix some screws and go back. I can understand that this astronaut on the picture wouldn't agree with me because he was repairing the Hubble Space Telescope, but this was exception which you will never get. So this is so important that those other points are related to this one. Therefore, the verification process is really important and really interesting topic. And Jakub will tell you more about it after that presentation. Because you need to be sure that every part, every subsystem, and every system, the whole system is like 100% ready. And I said it before, and I said it again, mass. This is really important. Because you need to provide a lot of documentation and provide everything to the prime contractor, for example. Then time schedule of the project is also a little bit different in the space sector, because when you have a satellite, you want to launch it. And when you want to launch it, you need to book a flight. And when you book the flight, you have some date. And you have to deliver the satellite within this date. Because when you don't deliver, you just lost money, and that's it. Because nobody, Elon Musk will not wait for you. Then other thing which is pretty unusual in other sectors is clean room. And you have to be able to integrate and test the satellite within this, let's say, environment. And the other thing, when we spoke about environment, the space environment is also a little bit different than down here. Because there is a really low temperature and also the high temperature. There is a radiation, which is changing with the orbit, by the way. And there is also vacuum. So you need to be sure that all those things your satellite withstand. and for some years, of course. Then there is other thing, and this is a mechanical image. On those pictures, you can see the impact of the really tiny part, which was like super fast. And it really doesn't matter if it's plastic or metallic part, it can do the same. So now, since I speak a lot, I have a little quiz for you, and whoever wins, I owe him a beer. So we have a picture here on the left side. We have solar panels, which are like unharmed. But on the right side, on the right picture, you can see that the panel is a little bit damaged, and it's because that it was hit by the particle which was smaller than the 5 millimeters in diameter. The speed of this particle was something about a few kilometers per second. So the question is, like, how big in diameter is this area? So what do you think? This is damage there. If you see the like, let's say, white circle, that's a damage.
About 15 centimeters.
15 centimeters, all right. Another guess?
1 meter.
What?
1 meter.
1 meter, all right. Somebody else? 40 centimeters, all right. So does anybody want to join this quiz? All right, so I owe you a beer. It was exactly it. Yeah. All right. So the damaged area is about 40 centimeters. And I think, like, I really like one picture which describes the space environment better than me, because you can feel like, or you can imagine how the satellite can feel in the space environment. This one. So we know about space environment, but we cannot also forget about the ground environment, because we need to manufacture it there, test it there, and transport it there. And when we talk about the transport, you also need to develop and design some jigs for it. We call it GSEs, which is short for the ground support equipment. And we do it by the truck, plane, or ship. So you can imagine that this is also like something unpleasant. And if you ask if it's like, because you see that there is also lunch, and you imagine that it's like worse than the transport by the truck, right? But you have to realize that the satellite is attached by the different points. So let's say the stresses and loads are a little bit different. And the behavior of the satellite is, let's say, also different. So you transport the satellite into the launch pad, and you put it into the rocket. You launch it, and you can imagine that there is a lot of like vibrations, acoustic noise, and static loads. So all of those have to like the satellite withstand. And after you reach the orbit, you need to separate the satellite from the rocket. That's also another thing, which is mechanical shock. So it's really, let's say, nasty environment also. And like I said before, sorry, you need to integrate or assemble and test your device in a clean room. And for those who don't know what clean room is, you can imagine it as a surgery room or operating room, because it's really similar. You have to wear the gloves, you have to wear some funny coats, and it's really clean environment. So we move to something more important, and that's the structure types. Basically, when we develop the satellite, we have, let's say, those three options, which is beam or truss structure, structure from machine parts, and composite or sandwich panel structure. I put those pictures just for better imagination. Don't worry, you will see some satellites. Beam and truss structure. Beam or truss is some element or part which is really long and thin. And when you put those parts together, you get some really nice structure which is, let's say, lightweight, and it can withstand a lot of stresses and loads. You can see the example in normal life by the construction crane. Then we have structure from machine parts, and machining is technology process which is based on removing material. So you have one block of aluminum, let's say, and you're removing material into the desired shape. Then we have a composite or sandwich panel structure, and the best example is, for example, a door with the filling. Now, you can see the structures here, and the upper ones are, let's say, the beam or truss structure. I think the left upper one is from Hubble Space Telescope. You can see that it's pretty light, and it can withstand a lot of loads. The other one, the structure from machine parts, is shown in the right lower picture. It's a really nice satellite from Blue Canyon, and you can see just by the eye that it's pretty rigid. And you use it, or the structure is used because you can attach some units and some subsystems into the panels. Then the last one, which is sandwich panel structure. You can see it on a plateau, and the sandwich panel. Those are the black parts, and I will describe it more in a detail, like in the next slides. So we know what the structure types are, and now I want to tell you some differences between small satellites and the big satellites, because there are some. You can see on the left side there is a CubeSat, which is a standardized sized satellite, which is like for about in this size. It's 34 centimeters high, and it weighs 12 kilograms. Just for your interest, this will be the look of our satellite roll. And on the right side, there is some huge monster which is called Plateau, which is like 3.5 meters high, and it weighs 2.3 tons. And you can already see some differences here. But there is one big difference between the big and small satellites, and that's the logic behind the development and design. Because the bigger satellites are usually made like in the logic that you have a payload, and you made a structure around the payload. So you can see the James Webb Space Telescope. There are some scientific instruments and mirrors, and then there are subsystems which are like placed underneath. Then we can see Hubble Space Telescope. It's basically one big camera, and the subsystems are placed in the middle sector. If your eyes are good enough, you can see the node with support system, and in this place there are placed like almost every subsystem. So you can see also in those satellites that every big satellite looks a little bit different, right? And also one common thing for those satellites is that they are usually made from the sandwich panel structure. On the other hand, the small satellites, as you can see, looks pretty much the same. You can see the difference here. Those are CubeSats, which are, like I said, standardized sized satellites. So the logic behind the small satellites is that you have some, let's say, standardized structure, and you choose the structure due to your payload. So you have some camera, and you can see that, for example, this satellite is small for my camera, so I will choose the, for example, Napadva structure, right? So this is, let's say, the difference. And also you can see that in small satellites, they are usually made from the machine parts, like you can see here. On the right picture, you can see it's an exploded view where the parts are machined, and then they just attach it together. That's it. And just again, for your interest, this is how the troll will look like. All right, so we can just move on. And there is another, let's say, division of the structure types. And we can divide it into the primary structure, secondary structure, and tertiary structure. One thing about the tertiary structure, it's not always the case that you have it. It's usual in the bigger satellites that you have some tertiary structure. And like the definition of the primary structure is that it's part of the structure that carries the main flight loads and it defines the overall stiffness. Then we have the secondary structure, which is structure attached to the primary structure with negligible participation in the main load transfer and overall stiffness. And then tertiary structure, which has it has no participation in the main load transfer. So in other words, when your tertiary structure fails, it basically means like almost nothing. There's just minor limitation. And but on the other hand, when your secondary structure fails, it has some like severe limitation for the mission, and you cannot do some tasks. And when your primary structure fails, it's just a game over, the mission is failure. There you can see some examples of the primary structure, secondary structure, and tertiary structure on those specific, let's say, satellites. And when I was talking about the tertiary structure, they are shown as a blue boxes, but it's, let's say, not the whole box. It's just the case for the electronics here. Because if the whole box like fails, the mission is over also. But if there is just some scratch or damage of the case, it's all right. And then on the right side, you can see the primary and secondary structure on the CubeSat structure. So now when we know what the structure type is, we can move on to the materials. And if you remember, on the requirements which are put it into the structure, mainly the strength, the stiffness, and the most important mass, it's logical that we have really limited choice when it comes to the material. So we basically use aluminum alloys, stainless steel alloys, titanium alloys, composite materials, and sandwich panel, or sandwich materials. So the most widely used, I would say, are the aluminum alloys because of their low density and good specific properties, and good corrosion resistance. Specific property is, you can imagine it as when you have like one part which is made from the aluminum and the other part made, for example, from the steel, and they are the same, they can withstand the same load. So the specific property says that the part from the, let's say, aluminum alloy is much lighter than the part from the steel, because it's, let's say, mechanical property like strength divided by the density. So another advantage of the aluminum alloy is that it's easily machinable. They are easy to procure because a lot of companies have it in stock, and also when it comes to the price, it's so cheap. But on the other hand, there is a lower strength compared to stainless steel and titanium alloys, also lower hardness. And we basically, in space sector, use the 3 series of the aluminum alloys. The first one is basically the clear aluminum. We use it for the thermal parts and the thermal dissipation. Then we have the 6th and the 7th one. They are used as a structural parts because of the edible materials of magnesium and zinc. So, as I said before, we use those materials for the panels, brackets, and structural parts, thermal parts. And the bracket is some part which you can imagine here. It is basically part which purpose is to attach 2 or more parts. Then we have stainless steel alloys. It has like better strength than the aluminum alloys. It's higher hardness, really good corrosion resistance, and let's say okay machinability. It's not so easy to machine it, but it's much better than the titanium, for example. And they are also easy to procure, and the price is affordable. So the logical question is like, why don't we use this instead of aluminum alloy? And that's what I was explaining before. There's the specific property. Because, for example, the density of the stainless steel is 3 times bigger or higher than the aluminum alloy. And we basically use edible materials like chromium, nickel, and mangan, which like added the stainless steel these properties. And as a use case, we use them sometimes for brackets, but it's occasional. And the main purpose is for the fasteners, which we called parts like bolts, nuts, and washers. Then the last metallic material is titanium alloys. An advantage, of course, it's higher strength than aluminum alloy. It has better hardness, and the specific properties are the best of those metallic materials. So you would like to choose it every time, but it's not easy to machine it, because as you can see on those left pictures, it's possible that the waste material will ignite. When there is a big friction, it can ignite, and that's not good. So therefore, you need machines with the cooling, and you need the machines which are stiff enough to be able to machine this material. Then also there is one disadvantage, which is the price, because it's really expensive compared to the other materials. Then we use this pretty widely, and it's for brackets and for the fasteners. Then first non-metallic material is a composite materials. And the composite is a material which is composed of 2 materials which have different mechanical properties, and when you put them together, it creates a really lightweight structure or really lightweight material with good specific properties. The specific properties are, for example, 10 times higher than from the titanium. So you really want to choose this material for your structure, because it has also good corrosion resistance. For example, most widely used one is carbon fiber reinforced polymers, which is carbon fiber. You can see it in Formula 1 cockpit, for example. and they are cured by the resin. And when you put those materials together, you get, like I said, really lightweight and good material. But on the other hand, it's not easy to make it because you need really good suppliers and providers, because there is really good, or the provider can make it bad, and there could be bubbles, and bubbles are in space are really a problem. So you need to have certified supplier. Also, when it comes to the price, it's really expensive. And we use this material for the brackets, panel sheets, and rods. As you can see on the picture, on the right side, this is we call central tube. This is central tube from the Plato mission, and like the whole part is made from the composite. And if you do it from the aluminum or titanium or stainless steel, it will be like really, it will more weight. Right. All right. Another one is sandwich materials. Sandwich material is a really interesting one, and you can really imagine it as a sandwich because you have, let's say, lower bread and the upper bread and the filling. That's the same thing. The lower bread and the upper bread, we call it skin, and the skin is made from aluminum sheets or composite material. Then we have the filling, which we call aluminum honeycomb core. It really looks like honeycomb. It's just the metallic sheets, the aluminum sheets, which are glued together and shaped into the honeycomb. So then you just put them together, glue them together, and you got something like you can see on the right picture. And the advantage, again, really lightweight material with good specific properties. And we use this for the bigger satellites, because you can, let's say, design a really big structure with really low weight. So now we know what material are used, we have some parts, and we have to attach it somehow. And for this purpose, we have some options, which are just, let's say, normal options, because we use bolts. They are easy to use, the accessibility is good, and they carry a lot of loads. But the disadvantage is that they weigh a lot. Like there is a certain percentage of the satellite, which could be, I don't know, for example, 10 or 20, which are caused by the fasteners. So you have to be aware, like when you use it and how many bolts you're using. Also, a really big disadvantage of the bolts is a heavy weight, like I said, and the price and delivery time. One example from the Plato, there were like 100 or 1,000 bolts, and each bolt was verified and packed separately. It has really every bolt has a sheet with the properties and the verification. So we can imagine that it can cost a lot. And to be more specific, like for example, one bolt for Plato costs around 100 euro. So if there are hundreds and thousands of those bolts, it can be costly. Then we have other method, and that's rivets. They are lightweight because the body is hollow, so you can save a lot of mass. Then the price is also more affordable, and they can also carry a lot of loads. But on the other hand, you need a trained personnel, because anyway, it can destroy your structure. Also, the accessibility is, let's say, much worse than in bolts, because you need special tools for the riveting. Therefore, you need some space for it. But anyway, we use it, and we use it for the attachment of the panels and brackets. And the last method is attachment via adhesives. It's also, let's say, lightweight method, and we can attach different materials with it. But on the other hand, it cannot withstand a lot of loads, and it's complicated for the manufacturing. Like I said before, there could be bubbles, and they are a problem. So we basically use it for the inserts, tie bases, and studs for grounding. And insert is a part which we put into the sandwich material. You can see it in the middle picture. It's just, let's say, aluminum part which is put it into the sandwich panel, and we can attach some units in it. The tie basis is, let's say, bracket. This one, you can see it here, and we can attach a harness with it. This is, for example, dispenser, and let's say it's kind of Frankenstein because there is every of those attachment methods, as you can see. So we got to the last slide, and if you remember, when Adam and Christina was talking about design phase or the phases in space sector, they start with the phase 0, which is basically feasibility study, and it ends with the phase F. This is called disposal. And development of the structure or for the satellite is mainly in phase B and C. Then after this design phase, it comes the verification phase. It's ongoing in phase C and D, and that's what will Jakub tell you more about it in the next presentation. So I thank you. And if you have any questions, and I know the answer, I will answer it to you. Thank you.
So, any questions?
I hope not. All right.
I just wanted to ask, you mentioned that the rivets can like damage your equipment.
The structure, yes.
Yeah, why is that?
Because, for example, we attach the composite material, which is, like I said, it's carbon fiber and a resin. And you put the rivet in it, into the hole, pretty little hole, and you have to, let's say, squeeze it, because the rivet works like there has to be some mechanical damage of the rivet to put the part together. So it gives load into the structure, and if there is, let's say, sharp edge of the rivet, you can destroy the structure. Okay.
You said before that the air bubbles are real trouble in composites. In rivets, when you squeeze them, don't you create bubbles sometimes as well? Is that a problem?
Phew. I'm not sure if you can make bubbles by that.
So basically squeeze both parts together.
Well, I don't think so, that you will make bubbles by that. I don't think so. But the bubbles are a problem, yeah.
When you showed the result of the debris impact on the structure, we were actually wondering how do the small satellites resist the debris? Because I couldn't see much protection on them.
Well, there are thousands of the, let's say, particles, for example, in a low Earth orbit. And if the particles is big enough, you have it in catalog, and the satellite can do a maneuver. But if the particle is small enough and you know nothing about it, you cannot track it, then you just pray. Your satellite has to withstand it. That's it.
And, with such a small satellite, we see, for example, the 5 mm debris that you showed on the solar panel.
Well, if I look at the picture, the damage structure was 40 centimeters, I wouldn't say so.
No, so that's fragile part since it is so permanent. I was wondering about the structure itself. So, for example, if it could break inside and destroy a small satellite completely.
It can.
Okay, thank you.
Any other question? If not, thank you, Ondřej, for coming,
Thank you.
for telling us more about structure. I think you deserve one more applause.
Okay, thank you.
And I think now is time for some beer. So go get one, and we will see here in, I think, 10 minutes. I will prepare myself and the presentation for you. So, thank you. Yeah, so again, thank you for coming. Thank you for staying here after on this presentation. And the next topic will be AIV and testing. So let's start. I hope it will work. Fuck. Huh. It froze somehow. Yeah. Yeah, it's working. I hope so. Yeah, so something a little bit about me. I am a lead of structural team at Space, although I'm not really into structure. So yeah. I'm a student of space applications at BUT. I also work in TRL Space for now as an intern, as a proposal manager. And I was also in Belgium at ESA Product Assurance and Awareness Training in May. Yeah, and some crazy things about me. I like music. As you can see, I like to spend time with my friends and yeah, something like that. Okay, so content of today's or mine presentation will be what the AIV, AIT and VNV means, then something about model philosophy, then there is one beer break, but we will see if you will need it because I'm not sure how it will be timing. And after that, we will go to talk about tests and documentations. Yeah, and I have 2 beer questions in my presentation. They are a little bit tricky, so yeah, be prepared for it. So what does those letters means? They means assembly, integration, test, verification, and validation. In other words, it's a process of turning a design into a real product. So you have something designed in your mind, computer, at papers, but you also need to really manufacture it and assemble it. So you want to create a real spacecraft, and most important word, working. You always want working spacecraft, not just something that doesn't work. Yeah, so what assembly means? It means that you are physically combining all those parts together and creating some bigger structure or larger entity. And what does integration means? Integration means that you are not only combining those parts together physically, but also you are combining them together so they can work together, they can communicate and be functional. And those 2 words, or those 2 processes, if you will take them, you should have like had a physical spacecraft. If not, somewhere is a problem. Yeah, and then what tests mean? Tests mean that you are measuring a performance or some characteristics of your spacecraft, subsystem parts. But the very important thing is that you are measuring them under representative conditions. Because if I can make some example, it's a really dumb example, but I think it will work. You want to know what's the weight of your structure. You don't want to measure it underwater because it doesn't make sense. Yeah? So something like that. Then what's verification and validation? It sounds very similar, but yeah, verification is a process in which you are demonstrating that the structure, the spacecraft, is free of defects and it's built, it's manufactured, it's produced in a specific specific way. It's produced according to specifications and is in some deviation and waivers. Validation means that it means that it's process in which you are demonstrating that the whole structure is working as it should work. It's really like it's working as your requirements are. Yeah, and what it's AAV responsible for, that whole satellite is integrable, testable, and flexible. If it's not integrable, it's not possible to assemble satellite. You know, if you have planned to put some big part into small hole, it won't work. So we always want to be satellite integrable. Testable, that means that you are able to test all the specifications, all the requirements. If you are not able to test some requirements, there is something wrong with requirements or with your design. And finally, flexible, that means that if something goes wrong, something breaks, it's easily accessible and you can change it. Okay. Let's look at verification approach, and there are three main questions: what, how, and when. What are you going to verify? Does anybody know? Yeah, requirements. How are you going to verify them? It's like, what can you use? You can use different methods. And when are you going to verify them? Are you going to verify them at the beginning of development, or at the end, in the center? When? It's different, and it's differ according to models, levels, and stages. So let's look not on what are you going to verify, because I think my colleagues have spoken a lot about requirements, but let's look how are you going to verify them. Firstly, inspection. In inspection, that means that when you get some part into warehouse, into your assembly facility, you are going to look at it and look for some defects, some misalignments, and something like that. We are going to measure it, but not like measure it like completely, but some simple measurements we are going to make. So firstly, look at your part or subsystem, system, spacecraft. Then you are going to make a review of design. That's the second thing you can do. So you can look at the documentations and compare if it's made how it should be or not. So yeah, you have to write the reviews. Then you can analyze. You can make analysis, some simulations, and other stuff. There is a lot of techniques and tools, so we are going to calculate things. And finally, test. So we are going to measure everything, if it's work how it should or not. And doesn't anybody know what should be here? It's a tricky question, but it's not for beer. Anyone? No? It's test. Yeah. So next question, when? When are you going to verify things? As I said, it depends, and the verification process is a little bit longer. It's not like 1 day, and yeah, verification takes place in like huge amount of time, or how can I say it? Like it takes place at different moments in product life, and some of the verifying processes or stages are qualification, acceptance, pre-launch verification, in-orbit verification, and post-life or post-landing verification. Yeah, so qualification and acceptance and pre-launch are before launch, in-orbit post-landing is after. Why are you going to verify something after landing or after you send your satellite into orbit? It doesn't make sense. But it makes sense because some requirements you cannot verify on the ground. You are not able to verify them here. You have to verify them in orbit or after landing, after post-life. And those requirements are maybe like, the example could be you maybe saw an Orion capsule from Artemis 1. Yeah, there were heat shields. How can you verify that heat shield will work? You cannot really on the ground. So they send it, the Orion, it made it all the mission, and then went back home, landed as it should land. Yeah, it doesn't blow up, so it's good. But they are still today verifying the heat shield. They are looking at it, they are making measurements, and so on. So some of the requirements you cannot verify on the ground before launch, and don't be scared if you found some requirements like that. But like, be careful about that, but don't be horrified or something like that. Yeah. Then what's qualification? Yeah. Qualification is a process in which you are verifying or demonstrating that your design meets the requirements, applicable requirements, with some qualification margins. It's first of the series of verification process. What the qualification margins are, I think Adam was talking about it in first presentation, but I will summarize it quickly. You want your subsystem work at specific like temperatures. You want that it should work, or the temperature should fluctuate from maybe 20 to minus 20 degrees Celsius. Okay. But the qualification margins, you want to be on safer side. So you make them more severe. So you will make tests on your subsystem, but you want your subsystem to fluctuate like from only -5 to 5, only to be safer. So that's qualification. After qualification, you go to acceptance. You want to accept your design that it's good without any errors, or like it really works as it should. So it's a process in which you are assuring that your subsystem part spacecraft is working as it should, is built in accordance with qualified design, so with design that was previously qualified from qualification, is free of workmanship defects, and yeah, it meets the specified acceptance margins. And are those more severe or less severe than qualification margins? That's second tricky question, still not a beer question. More or less? Anyone? No one? More severe. You said more severe, or who said? More severe, yeah? No, they are not. The most severe margins are qualification margins. The acceptance margins are more severe than actual environment, but less severe than qualification margins. Because you already qualified the DA, it can withstand some margins that are more severe. Now you are accepting something, and you are like light on it. Yeah, and so let's make some example how it works. We have some CubeSat with different subsystems, and I will now focus on AOCS. It consists of reaction wheels and magnet torquer. So you want to go through the process. Firstly, you will do qualification of reaction wheels and magnet torquer. After you qualify those two, you can qualify the whole AOCS, but still not the whole CubeSat. Be careful about it. After you qualify whole AOCS, you know that, okay, it worked, so let's make acceptance. So you make acceptance of reaction wheels, magnet torquer, and then the acceptance of whole AOCS. And if you have acceptance of all subsystems, then you can try to put them together into CubeSat and firstly qualify whole CubeSat and then make acceptance. Does it make sense? Yes. Thank you. Okay, so yeah, there is a different visualization of it. It's V of verification. You can see that from the beginning of the mission, you are going more into more details until you hit the ground. That's software, hardware, parts. You design the parts, and after that you are going up. So we are going to qualify parts, then qualify subsystem, then acceptance, make acceptance, and so on, so on, so on. So yeah, do we build directly the spacecraft that will fly? You can, but I wouldn't do it. So let's look at the model philosophy. There is a lot of models, like structural model, thermal model, engineering model, qualification model, flight model, proto-flight model, avionics test bench, and many, many others. But why? That's the question. Because you want to reduce the risk. Always reduce the risk. Because as Ondřej previously said, you cannot really repair something in the space. Like, yeah, there was one time, but it's really, really expensive. And which model should you use? Like, there is many models, but each product has its own model philosophy. Sometimes you need engineering model, sometimes not. Sometimes you need thermal model, sometimes not. Yeah, so let's look a little bit closer to those models. So structural and thermal model, it's representative of design, physical and thermal, and structural. It's representative of their properties, but also it's not really like detailed. It's made from like dummies of lower level subsystems. Dummies, like they are pretty close to the real thing. They have pretty like similar properties, but they are not the same. Yeah. So why should you use structural and thermal model, or for what? This model is used for qualification and verifying finite element model and thermal mathematical model. So all those simulation you made previously, or you are still making them. And also it's used for validation of MGSE, so mechanical ground support equipment. Then engineering model is also some kind of representative in form of function, and like it's already functional, but you are not using real components that you will use in space. You are using less reliable parts and usually without redundancy. This model is used for functional qualification and verification of electrical and software interfaces, and also for EGSE, so electrical ground support equipment. Yeah, then avionics test bench. It's composed of engineering model or qualification model. Still, you want to see functional model that's really functional, but it's not. It's little bit like it's not built in form of spacecraft, but it's like subsystems only connected via wires and some other attachments. Yeah, and there is like second word for this test bench, avionics test bench. Does anybody know what's the name? You heard it already, maybe in other presentation. It's flat set, if you remember. Yeah, and the flat set is used for functional verification and debugging of some software errors or other errors. Yeah, and finally, or not finally, it's not the last model, it's qualification and flight model. Both of them are fully representative, so full redundancy. There are real parts, not space-graded parts, but real parts. And yeah, so they are like fully representative. But what's the difference between them? The qualification model is used for qualification. Yeah, it makes sense. And flight model is used for acceptance. You are not using, in this model philosophy, you are not using one model for both of them. But there is one philosophy, it's proto-flight model, and this is fully representative model, and it's used for proto-qualification. It means that it's like, it's not that severe, it's a little bit lighter on the spacecraft, but you're using same model for qualification and acceptance. Yeah, there is a much higher risk, or yeah, higher risk, but you are not using proto-flight model in cases when you are making some really big satellite that nobody ever done before. You are using this model philosophy when there is a reasonable design heritage or experienced system developer. So we're using maybe some off-the-shelf components and so on. Yeah, and the advantage of this model philosophy is that it's cost and schedule reduction. That's the advantage. Yeah, And so first beer question, what is the best model philosophy?
It depends.
Who said it? Any other thoughts?
ABC.
AB.
Give options.
Like you saw the options.
Well, the one that fits your requirements and possibilities.
Yeah, that's the right question. We both have beer on me because
We can have it.
yeah, it depends. It depends. You have to decide what's the best option for you. Always it will be different. So yeah. Yeah, and I have a beer time here scheduled, but I can make it to the end, maybe. It will take probably 20 more minutes, so it's up to you.
I would continue.
Yeah, continue. Okay. So let's look at tests.
Like if we vote, I'm continuing.
We are not voting because. Yeah. So why tests? Because there are many questions. Will we survive the launch? Will we survive in outer space? Will we function and perform correctly? And will we fulfill requirements? You always want to answer to these questions, and that's why you are going to test your system, subsystem, spacecraft. So what is waiting for us when you want to launch your satellite into orbit? There is acoustic noise, vibrations, static loads, mechanical shocks, radiation, vacuum, debris. Basically, everything wants to kill you, and you want to survive. So that's what death is waiting for you, basically. Like,
Feels like Australia.
yeah, yeah, feels like Australia. Yeah. So yeah, will we survive the launch? Let's look at all those things. Acoustic noise, it's not like you have like speakers next to your spacecraft or something like that. Yeah, the noise is in form of pressure waves. So it's pressure fluctuations. And it's a really specific thing for big satellites, because acoustic noise are pretty special, and you are going to test them only on some bigger or larger surfaces. And for this, you have a reverberating chamber. You can see it on the picture. And you use also accelerometers as an instrument of testing. Yeah. So that's first thing. Then there is vibration, and in form of sinusoidal or random. You have both of them. You are testing it via shaker and also with accelerometers. And at the vibration, there is one specific thing that you firstly test low level sign, then go through the high level and through the random, and then again through low level, because you want to see, or you want to check if some degradation is there or not. Then static load. It's basically made from the rocket itself, because you are accelerating, and yeah, it makes a lot of load on your spacecraft. For this you are using test YIG or something like that. I cannot pronounce it right, probably. And yeah, for CubeSats or for CubeSat structures, if you are using some off-shelf structure, you don't really need to test that, because already before someone tested it. And yeah, so something like that. And you can see some graph. So you can see there that maybe somebody see, but somebody not. If rocket start, there is like quick acceleration, so quick load. It's going up, then a little bit down because you are in max Q, so maximum pressure load on the rocket. So the rocket will a little bit slow down or will go down with thrust, and then again up, and then you can see that there is a quick drop, and it's when the first stage will cut off and the second stage will start. So then you are again accelerating, and then again quick drop because the second stage was cut off. So you are simulating really the start of the rocket here. Yeah. Then you made it through the start of the rocket, and you are in outer space. There is a vacuum, so you have problem with thermal. So you make thermal tests. And there are two tests, thermal balance and thermal vacuum test. Thermal balance is cycling, it's thermal cycling and stability test. Thermal vacuum, in thermal vacuum test you are looking at the performance of your spacecraft in vacuum and in thermal conditions like in space. They are performed in thermal vacuum chamber, and you are not more using accelerometers because it doesn't make sense. You are using thermocouples. Yeah, and there is a lot more of tests. As you can see, there is test for COG, so center of gravity. There is test for EMC, test of deployable arrays, and many more. Yeah, and so how the environmental test campaign looks like? What are you going to do first? What you are going to do as last? Yeah. So firstly, yeah, you came to testing facility. You unpack everything. Maybe assemble your satellite or something. Then you will make some pre-test functional test if everything works, because you can bring a not working satellite and then you are going to test it. It doesn't make sense. You make pre-flight, pre-test test, let's say. Then you will attach accelerometer, then go to sine vibrations, then make a functional test, then go to random vibration, again functional test, then you will take out the accelerometers, install the thermocouples, and you are going to TBTV, so thermal balance and thermal vacuum test. Then you are going again for a functional test. If everything works, then you are going to uninstall the thermocouples and go for EMC test. And after that, you have SVT. I forgot what does it mean, but it's some kind of test. Sorry for that. And then for a post environmental test campaign, functional test. So you are going to look if everything works. And there is one golden rule. Why it's going like that? Why you are going from vibrations to maybe some shock test, and then to vacuum and EMC. And the golden rule is shake it before you bake it, because you want to go through the test as the spacecraft will go through all those hazards. Yeah, so that's for the tests. And I already said something about ground support equipment, and it's part of work of space engineers. You are not only designing all those spacecraft subsystems and stuff like that. You always want or always need some ground support equipment. So there are mechanical ground support equipment, so maybe some stands, boxes for transportations and stuff like that. Then there is electrical ground support equipment, so for electrical tests and stuff like that. You sometimes want to simulate one of your payload because you don't have the payload developed yet. So sometimes some of those equipments really simulate the power consumptions and they are generating some data. I also saw or heard about one equipment that was like maybe 3 by 5 meter of really 3D model of the moon's surface, just to verify the navigation system. So camera was going above this surface, this modeled surface, and was trying to not guess, but trying to tell you where you are. And so you maybe sometimes you make some cool stuff like that, but not always. Also, optical systems need some support equipment, so some like cubes for calibrations and stuff like that. Also, very dangerous thing, fluid like the thrusters and rocket engines are very dangerous, so you need some support equipment for that if you are going to like fill it up. And you cannot forget about some basic stuff like clothes, heads, and screwdrivers, and everything you can see here. Yeah. So I have second beer question. Is there something we should do before testing? And I haven't mentioned it yet.
Can you be more specific?
I don't want to be. Yeah, there is a lot of things, but imagine you are in the test facility, you have everything prepared, you have whole spacecraft, you have all the equipment.
Test procedure?
Yeah, test procedures. So you need documentation. I think everybody here was on some labs or something like that, and you got some procedure, and then you had to write some report or something like that. So that's also here, and that's a very important thing. So there is a lot of documents. You have some plans, specifications, procedures, reports, schedules, and then some like final conclusional like document. And why do you need such procedures and the reports, like maybe integration procedures? Why do you need them? That's good question. And you need it because there is one video, and I hope the Wi-Fi works. It doesn't work. Yeah, sorry for that. But maybe you heard, about it was a Russian rocket. It started and then just turned around and went straight to the ground. Like it was up and down. And there was one thing, and it was not like a mistake in procedure or something. There was procedure for that, but someone who was installing the accelerometer installed it upside down. So, and what's more important, it was like vertical accelerometer. So the rocket started, but thought that it's going in opposite direction. And it's like, why? I want to go up, not down. So it's tried to change the course, so it made whole, like it steered and went to the ground.
But
Yeah.
the Russian rocket, so it's normal.
I wouldn't say, because Russians have also Soyuz, most reliable rocket ever known, probably. Yeah, it's really old, but what? Yeah, yeah, okay. Yeah, it is most, but most used before 2020, maybe like that.
How many RUDs had Soyuz experience?
How many what?
Like rapid unscheduled disassembly.
I don't know that. But yeah, like there was procedure. There was, I think, also labels that this side up or something like that. But I don't know how someone installed it in opposite direction, and it was like pretty big mistake. So yeah, what's the documentation flow? You have some system requirements, then you made some verification plan, again AIT plan, and from AIT plan you make some test specifications. So what are you going to test? What are you going to measure? Yeah. And from test specification, you will make test procedure, you will go through the test and make test report, and finally all the test reports and everything will go to verification control document. Yeah, so how the test looks like from documentation point of view. So you have some test preparation phase. Before test, so we are making all those procedures and maybe some you prepare documents for reports. So anyone is making the test will only fill all the needed places. Then you have test readiness review. So you verify that everything is ready for the test campaign. If yes, you're going through the test campaign or test execution. Then you have a post-test review, so you are going to look if you made everything you had to make or something like that. And then you go to write all those reports, and then at the end there is test review board, and test review board is pretty crucial. It's meeting where all the guys will meet and agree or disagree on the results of the test, and will like close test campaign or make some additional tests. So yeah, and what if something goes wrong? What if you measure something and it doesn't comply with requirements? Yeah, so what to do? There is always product and quality assurance guy, or it should be. Yeah, and ISA is pretty strict about it. Yeah, so you need PA or QA. PA and QA they are really, they should be independent, and those guys you hate always, because they are always complaining about something, that you made some mistake here, that you made some mistake in documentations and something like that. But that's their work, and they always check everything. And if something goes wrong on the test or something is not like it should be, there is a non-conformance report. You will open this report, you will fill this, write down. The main goal of this report is to find the root cause of this problem, identify it, and decide if it's okay, if it didn't went how we wanted to, but it's not a real problem. So yeah, you can make it like that and go with launch. But sometimes not, and sometimes you need to make some changes. And all those NCRs should be closed before launch. That's really important. Yeah, and I think with this I will end this presentation. Remember that you need to write all those documents. You need to prepare for testing in advance, and don't hate PA guys too much. Yeah, so thank you for your attention. Yeah, is there any question for me? No?
I have a question.
Okay.
Why do you test for acoustics?
You are not testing always for acoustics.
But if
Why?
you do, why?
Because around the rockets there is a lot of noise and those pressure fluctuations, and especially larger surfaces have problem with that, because from the acoustic noise you can get some vibrations, and vibration can lose some screws or make some damage to your equipment. Yeah, but you can
But isn't it
on
meant-
smaller spacecraft you can make only vibration tests and not acoustic tests.
But isn't it mainly protected by fairing?
It is, but
Closed
it's
fairing,
fairing is. I don't think the fairing is sealed.
Co fairing?
Takový, no máš
Kryt,
tam
kryt.
a pak máš tu slupku, co je na...
Obal.
And even if the fairing is sealed, you know that fairing is not like really stiff and robust, and has some can like a little bit bend or something and make some pressure fluctuation inside.
Okay.
I think. Any other question? Yeah?
Have you attended such a measurement test?
No, I haven't yet. I talked about it, but I didn't.
I have another one.
Okay.
Well, I didn't really get what's the difference between the flat set and engineering model.
Flat set, you have all the subsystems on the like table,
Yeah.
but in engineering model you have it in like spacecraft shape, I would say. And in engineering model you don't have all the redundancies and so on. Like flat set is used mainly for software testing. Engineering model can be used or is used for qualification. Or other tests like COG and so on. Yeah, not the qualification, but
I understand it like in engineering model you just looking if each parts are, because it's kind of complex.
Yeah.
So if each part is operating with other part, just
Yeah.
see if is it okay, design is okay.
and physically if it's okay. Any other question? Yeah.
So you test for vibrations,
Yeah.
and you test for heat. Don't you test the combination? Imagine this transmitter wax.
Like, not really, because that's the thing about the shake before you bake it. You are firstly going through the vibrations, through the mechanical shocks and all those things, and then you get to the space. And at the start, the satellite is not working, so it's not generating any heat and stuff like that. So you don't really need to. But
For re-entry.
like, yeah, for re-entry it's pretty.
It's shaking and heat.
Yeah, but all the spacecraft already went through both of them, and like it's pretty, like with that it's pretty special, and I would say that you cannot really do that on the ground, because it's firstly too cost and will take you a lot of time. Yes, or too expensive. It's so. I don't know about any facilities that have vibration plate inside thermal vacuum chamber because it's like really like I cannot imagine that. But yeah, re-entry is a little bit different, and that's also why something you cannot test on the ground, but post landing and in orbit. Any other question? If not, thank you for attention. Thank you. Yeah, thank you for coming. Have a nice end of the day. Go grab some beer, and if are there guys from structural team, please come to me. And also, I cannot forget that I was in Bremen last week at the Tech Expo, Space Tech Expo, and I brought some goodies for you. So you are lucky that you are here today because I have some stickers and stuff like that from the company. So you can come here and grab something.